There is a problem so difficult that the fastest supercomputers on Earth cannot solve it perfectly. Engineers have spent decades trying. Mathematicians have built entire careers around it, and it sits at the core of how we route the internet, schedule airlines, coordinate surgical robots, and design the cities we live in. It is called distributed optimization, and bees cracked it 45 million years ago. Not approximately, not partially, with a level of reliability that when researchers at Cornell finally measured it, made them go back and check their math. Because the answer kept coming out better than it had any right to be. 50,000 insects, each one with a brain smaller than a sesame seed, no leader, no map, no shared memory, converging on the optimal solution to a multivariable search problem faster and more accurately than algorithms we built with modern computers. If you close this video right now, you will spend the rest of your day not knowing why that is possible. And I promise you, the reason is stranger, darker, and more beautiful than anything you would guess. There is a moment in the life of a honeybee colony that scientists call the swarm. It happens in spring, when the hive has grown too large to sustain itself and the colony must divide. The old queen leaves with roughly half the workers, tens of thousands of bees, and they cluster together somewhere temporary, usually hanging from a tree branch, while scouts go out to search for a new home. Now here is what makes this extraordinary. Nobody is in charge. The queen does not direct the search. There is no committee, there is no vote in any conventional sense. And yet within hours or days, 50,000 organisms with a combined brain mass smaller than a grape will reach a consensus so reliable, so consistently optimal, that it has been studied by computer scientists trying to build better algorithms for routing internet traffic, optimizing delivery systems, and coordinating fleets of autonomous robots. The bees, in other words, figured out distributed decision-making millions of years before we knew it was a problem worth solving. If you find that as fascinating as I do, hit that like button right now and subscribe. This channel digs into the real science behind nature's most mind-bending engineering solutions, and we are just getting started. To understand what is really happening during a bee swarm, you need to understand a concept called stigmergy. It is a form of indirect communication where individuals respond to changes in the environment rather than to each other directly. Termites use it when building their mounds, ants use it when laying pheromone trails, and bees use a version of it that is uniquely sophisticated, because their environment is not the physical world around them, their environment is the swarm itself. When a scout bee discovers a potential nest site, she returns to the cluster and performs what Carl von Frisch, the Austrian ethologist who won the Nobel Prize for decoding it, called the waggle dance. The dance encodes the direction, distance, and quality of the site she found. The better the site, the longer and more vigorous the dance. Other bees watch, evaluate, and then go investigate the sites for themselves. If they agree that a site is excellent, they return and dance for it too. If it is mediocre, they dance less. Eventually, through this cascading process of recruitment and reinforcement, the colony converges on a single location, and studies have shown that it is almost always the best available option, even when there are dozens of competing sites to evaluate. This is not luck. This is a mathematical process that computer scientists recognize as a stochastic optimization algorithm, specifically, something close to what is now called ant colony optimization, or ACO, even though the bees were doing it long before anyone gave it a name. Now here is where it gets genuinely unsettling in the best possible way. The individual bee has no idea what the optimal nest site is. She cannot evaluate all the options. She has not seen all the sites. She is working with partial local information, and she is biased in a sense toward whatever she personally found. And yet the group gets it right. How? The answer lies in the inhibitory signals that bees use to dampen excessive enthusiasm. When a scout returns and starts dancing for a site, other scouts who have visited competing locations will approach her and butt their heads against hers in what researchers call a stop signal. This acts as a brake. It prevents any single scout from dominating the decision-making process prematurely. It is in every functional sense a check against misinformation. The colony has built into its behavior a mechanism for epistemic humility, for not committing too fast to the loudest voice in the room. Scientists Thomas Seeley and Suzanne Kuhnholz at Cornell University documented this in detail, and the implications are striking. The swarm is not just optimizing for a good answer, it is optimizing for a robust, well-verified answer. There is a difference, and the bees know it at the collective level, even though no individual bee does. Let us pause here and consider the scale of what we are talking about, because the numbers matter. A single honeybee brain contains approximately 1 million neurons. For context, A human brain contains roughly 86 billion, so a single bee is operating with about 100,000 times less raw processing power than you are right now. And yet 50,000 of them together are performing what engineers call parallel distributed processing across a dynamic decentralized network, with no server, no central processor, no overseer. When researchers at Georgia Tech and at universities in the United Kingdom began modeling this behavior mathematically, they found that the swarm's decision-making architecture closely resembles the way neurons in a mammalian brain reach consensus during perceptual decisions. In other words, the way a bee colony chooses a nest site may be structurally similar to the way your brain decides what you are seeing when you look at an ambiguous image. The swarm is not just a metaphor for the brain. It may be a convergent evolutionary solution to the same fundamental computational problem. How do you make a reliable decision using unreliable, incomplete, locally gathered information? That question is at the heart of everything from neuroscience to artificial intelligence, and bees have been answering it for at least 45 million years. This is the point in the story where the science stops being a curiosity and starts being a blueprint. Engineers and computer scientists have been paying very close attention. The field of swarm intelligence, formally established in the 1990s but drawing on decades of biological observation, uses the principles of bee and ant behavior to solve what are technically called NP-hard problems. These are problems where the number of possible solutions grows so fast with scale that no computer can evaluate all of them in a reasonable time. Things like the traveling salesman problem, where you must find the shortest possible route through hundreds of cities, or the problem of scheduling thousands of flights through a hub airport with minimal delays, or coordinating the movements of a search and rescue drone swarm across collapsed terrain after an earthquake. In each case, algorithms inspired by bee swarm behavior outperform many classical approaches, not because they find the perfect answer every time, but because they find excellent answers very quickly, using distributed agents with local information, just like scouts returning from potential nest sites. Marco Dorigo, at the Université Libre de Bruxelles, has been one of the leading figures in formalizing these algorithms, and his work on ant colony optimization and related systems has now been applied in telecommunications networks, logistics, robotics and drug discovery pipelines. Real systems, real applications, solving real problems because someone decided to take insects seriously. If this is the kind of content that makes you think differently, share this video with someone who needs to see it. The science we cover here deserves a wider audience, but let us not get too comfortable with the success story, because science, real science, includes the parts that do not fit neatly into a narrative. There are aspects of bee swarm intelligence that remain genuinely puzzling, and that push back against easy explanations. One of them is what happens when the swarm makes a bad decision. It is rare, but it happens, sometimes under time pressure or in degraded environmental conditions. Bee colonies have been observed selecting suboptimal nest sites, sites with insufficient volume, poor insulation, or entrance holes that are too large to defend against predators. In these cases, what failed was not the algorithm itself, but the quality of the input. The scouts gathered poor information, or external stressors, cold, rain, predation, compressed the time available for the consensus process to converge. The swarm is robust, but it is not infallible, and this is a critically important distinction, because it tells us something profound about the nature of collective intelligence. It is only as good as the information environment in which it operates. When that environment is degraded, even the most elegant distributed system can fail. This has direct implications for how we design AI systems, distributed networks, and some researchers argue speculatively, though it is worth noting, even human social institutions. The bees did not engineer their system to be perfect. They evolved it to be good enough, often enough to survive. There is one more layer to this story that almost never gets discussed outside of specialist journals, and I think it is the most remarkable part of all. When a honeybee colony is in the swarm cluster, hanging and waiting while scouts make their decisions, the bees at the interior of the cluster are generating heat. They vibrate their flight muscles to maintain the cluster temperature, burning through energy stores they cannot replenish because they are not foraging. This means the swarm is operating under an energy budget, a hard deadline imposed by biology. If the decision-making process takes too long, the bees begin to run out of fuel. This is not a small constraint. It means that the entire decision-making architecture, the dances, the stop signals, the quorum sensing that finally commits the swarm to one location, evolved under selection pressure that rewards not just accuracy but speed. The system had to be fast enough to decide before the swarm starved, and accurate enough to select a site that would allow the colony to survive the following winter. That dual pressure, accuracy and speed, simultaneously, is exactly the kind of constraint that engineers face when designing real-world systems. And bees resolved it through a mechanism so elegant that when Thomas Seeley described it in his 2010 book Honeybee Democracy, the reaction from the engineering and computer science community was, by multiple accounts, something close to awe. Picture this for a moment as a visual: a single bee landing on a branch in a forest. The sun is low, the air is still, then one by one thousands of others arrive, until the branch is covered in a living, breathing mass of amber and black, pulsing gently with shared heat. Somewhere inside that mass, information is moving. Dances are being performed on the surface in tiny arenas of light. Decisions are being made, without any one creature knowing it. The branch bends slightly under the weight of 50,000 futures, all pointing in the same direction toward a home that does not exist yet but will, because the mathematics of their behavior demands it. That image is real. That is not poetry. That is biology, and it is happening in fields and forests right now, invisible to almost everyone. We are at a point in the history of technology where the gap between biological intelligence and artificial intelligence is being bridged, not by making machines think like humans, but by making machines think like bees. Swarm robotics laboratories at MIT, ETH Zurich, and Harvard's Wyss Institute are building systems of simple robots that individually do very little, but collectively can build structures, explore unknown terrain, and adapt to damage, all without central control, all using principles derived from insect behavior. In medicine, researchers are exploring whether swarm algorithms can help navigate nanoscale drug delivery within the human bloodstream. In space exploration, proposals have been made for deploying swarms of small probes to explore planetary surfaces collaboratively, sharing information in real time through bee-like signaling protocols. None of this is guaranteed. Much of it is still speculative, still in the proof of concept stage. But the direction is clear, and it is pointing at a tree branch in a spring forest, covered in bees who figured this out 45 million years ago, and never stopped. The bee does not know it is solving a hard computational problem. It does not know that its dance encodes vector mathematics. It does not know that the stop signal it delivers is an epistemic correction mechanism. It knows only what evolution has given it, a set of behaviors, finely tuned by deep time, that work. And that is the final quiet terror of this story. Not that insects are secretly intelligent, but that intelligence itself may not be what we thought it was. It may not require a central processor. It may not require consciousness. It may not require anything more than simple rules, applied consistently by many agents, in a world that rewards good solutions. If that is true, and the bees suggest that it is, then the line between the swarm and the brain, between the hive and the city, between the dance and the algorithm, is thinner than we ever imagined. And it was always a bee that was dancing on it. Subscribe if you want to keep exploring the edge of what science knows and what it suspects. There is so much more where this came from.